In this example, we're going to estimate the sensitivity of the period of a pendulum in seconds to a mistake in its length. So when we initially calculated this period, we thought that the length of the pendulum was 2 meters, but when we measured it really carefully, we learned that the pendulum is actually only 1.99 meters, and presumably that doesn't make too much difference, but we'd like to estimate just how much difference that does make. So if L is 2 meters, and if we set the gravitational constant to just 9.8 meters per second, which is a pretty common approximation for that constant, we get a time period of 2.8 seconds. We've learned that L is actually 1.99 meters. So the difference in t that occurs because of this change in L is approximately just the slope, the rate at which t changes when L changes a little bit, times the small change in L that we have. And so we need to find this value, t sub L of 2, and actually we found t sub L the other day in class. So it turns out that t sub L evaluated at L equals 2 is about 0.7 seconds per meter. That yields a change in the period that's about 0.7 times negative 0.01, where this is the difference between our correct value of 1.99 and the value that we actually used for the calculation of 2. This leads to a pretty small correction, negative 0.007 seconds, so thousandths of a second on each period. One potential application of a pendulum is that it might be being used to keep time. So we might be interested in how off our timekeeping gets if we're using this pendulum to figure out an hour. Our pendulum takes 2.8 seconds to complete a swing, so it swings 60 divided by 2.8 times per minute. This is about 21 times a minute. This corresponds to about 1,270 swings in an hour. So the number of swings in an hour is about 3,600 over the length of a period, and we can ask how this number of swings that happens in an hour will change given that the period is changing. We can again apply the differential to figure out the change in n. So the change in n is just going to be the derivative of n at the original value of t times the change in t. And notice that this derivative was negative and the change in t is negative, so we're going to have more swings. That's what we expect because the period got shorter. Substituting in some numbers, we learn that there's about 3 more swings happening in an hour. So if this pendulum were a pendulum and a clock, our clock would be getting very slightly off every hour.